This video is going to introduce us to the concept of simple harmonic motion, spring, and pendulums in regards to AP Physics C. This is the first of two PowerPoint slides. Okay, we're going to review some learning objectives and essential knowledges. In particular, pay attention to the formulas on the right-hand side. Okay, these formulas are both on the formula sheet, and we'll go over them as we talk through this PowerPoint. Okay. Again, essential knowledge, we're going to be incorporating calculus in this. In particular, look at the formula on the bottom. This formula is very important. It basically says that acceleration, which is the second derivative of position with respect to time, is going to equal minus omega squared x. Okay, omega is that same omega that we used in rotational motion. Okay, so it's angular velocity, and we'll see how that works. Okay, here's a few more information on the essential knowledge on the lower right-hand side. We see what kind of limitations AP Physics C puts on us, and we'll go through that as well. The remainder of these essential knowledges is primarily focused on energy. Okay, this is the formula for potential energy, 1/2 kx squared. This is the potential energy for a spring. And we'll see how to do that, but energy is reserved mostly for the next set of slides. Okay, this slide continues the discussion on energy. We have a couple more formulas that are on the formula sheet. You should be familiar already with the kinetic energy formula, which is 1/2 mv squared. The same formula for the spring energy, and that total energy is going to equal kinetic plus potential. Again, you should be aware of that, but the fact that these formulas are here, I've highlighted them. They're not on the formula sheet, but they're very important, and again, we'll see that in the next set of slides. Okay, lastly, we have the period formulas. We're going to go through the derivation. It's more important to go through these two and be able to derive these than to memorize them, especially since they are on the formula sheet. Okay, the Hooke's law, which is the restoring force is equal to minus k delta x, is also on the formula sheet, but we'll see how that works into this unit. Okay. So just as a comparison, these are the formulas that are associated with simple harmonic motion on the IB formula sheet. Okay, they're very similar, but there's slight differences, and we'll see how the combination of these two could be very useful. Okay, just to go over a few definitions, we should be familiar with most of these already. Period is the time required for one complete back and forth motion. Sometimes you do need to be careful. The questions give you only 1/2 of the motion, and you need to realize that you need to go a full back and forth. A period is measured in seconds. Frequency, however, is measured in 1/seconds. This is the number of back and forth motions in 1 second. Okay, we also use the units of hertz for frequency. Equilibrium is going to be the midpoint of the motion. At this point, force and acceleration will both equal 0. Net force and acceleration equals 0. Then we have amplitude, which is the furthest distance from equilibrium. And oscillation is repetitive back and forth motions. And simple harmonic motion, which is what this unit is a special type of oscillation. Not all oscillations are simple harmonic motion. Okay, so just to review on period and frequency, they are inverses of each other. So T is equal to 1/f, and F is equal to 1/t. What that basically means is that once you know one of them, you know the other. Okay, and both of these are going to be related to omega. Okay, because omega is going to be equal to 2πf. We see the dimensional analysis associated with this. It turns into radians per second. Remember that radians is not really a unit, so it's still 1/seconds. Okay, so it's omega is going to equal 2πf or 2π/t. So once you know any of these three, omega, t, or f, you can effectively calculate fairly easily the other one. Okay, so it's important to remember that these three are related. Okay, well, simple harmonic motion is going to be a special type of oscillation where the acceleration of the object is 1, proportional to the object's displacement from equilibrium. So the farther it is from equilibrium, the greater the force, and it's going to be proportional. And the direction of that acceleration is towards equilibrium. Okay, so it's always what we describe as restorative, always trying to get back to that middle point. Mathematically, it turns into acceleration is equal to minus some constant k times x. I probably shouldn't have used the letter k there because k is what we would use for the spring constant, but I'll have to fix that in the next iteration. Also remember that acceleration is the second derivative of x with respect to time, the first derivative being velocity. So the fact that we have the second derivative of a function is equal to some constant, negative times some constant times that function. Okay, so second derivative of x is equal to minus kx. The only function that we know of whose second derivative equals itself with a negative sign involved is the cosine sine function. Okay, so we're basically going to state that x is equal to some amplitude a times cosine omega t plus phi, where phi is some phase shift. Okay, we're not going to be too worried about the phase shift, but just realize that a sine and a cosine function are effectively the same thing, just depending on where you start. Okay, so what is that phase shift? Okay, so here I have a sine function. It starts at 0, goes up, comes back down, and repeats forever. Okay, from this we can definitely get the concept that, okay, somewhere around a little bit less than somewhere around 12 and a half seconds is the period. My amplitude is about 4, but in particular, let's see what happens if I shift it in time. So that's what we're describing as the phase shift, okay? And if I shift it a total of pi over 2, we end up with the cosine curve. So the blue line here is the cosine, the red line is the sine. Okay, this is very useful more when we're talking about wave interference, as we did sophomore year, but we're not really going to get into that this year in AP Physics C. Okay, if I move it even further to a phase difference of pi, or basically half a wave, then I end up with this situation where you would have complete destructive interference if these two waves were to collide. Okay, but again, we're not too worried about that here in AP Physics C. Okay, so that whole aspect of sines and cosines is also relating us to uniform circular motion. So here on the right, I have an object. The green dot is basically just moving in a circle at a uniform speed. On the left is a mass going up and down. If you look at the point of the green dot on both of them, they're pretty much at the same location vertically. So in the circle, we could say that y of t is equal to r times cosine omega t. Okay, we've seen that in math class, and the same thing here. So on the spring, we can basically say the same thing, except instead of r being the radius, a is the amplitude, but it's pretty much the same concept. From math, okay, we can say, well, when omega t is equal to 2 pi, that's when our period exists, okay? So solve for t in that case, and t turns into 2 pi divided by omega. Okay, so one of the most common systems that we'll be using to investigate it is the mass spring system. The reason is this is an exact situation where F is equal to minus kx, or A is going to be some constant, negative constant, times delta x. So here's the derivation of this, okay? We basically say with F is equal to minus kx, Newton's second law therefore says ma is equal to minus kx. Calculus tells us that acceleration is the second derivative, and so we end up with minus k over m delta x. Next step, we basically guess, okay, or state that x of t is a amplitude times cosine omega t. Take the derivative once, take the derivative twice. So a of t is equal to minus a omega squared cosine omega t. So we set them equal to each other, okay? And so here we have it. Okay, a of t is going to equal minus omega squared a cosine omega t. But we already said that A cosine omega t is x of t. So we substitute that back and we realize that A of t is equal to minus omega squared x of t. But A from above is also equal to minus k over m x of t. What that basically says is omega squared equals k over m. Taking a square root, omega is equal to the square root of k over m. And period, which is equal to 2 pi over omega, turns into 2 pi times the square root of m divided by k. And that's the derivation of Hooke's law. Okay, I mean, that's the derivation of the period for a mass spring system. Okay, bigger mass, bigger period. Okay, because it takes longer. Bigger k, quicker period. Shorter period. Here's the situation for a pendulum, okay, the other most common HHM system that we'll investigate. Okay, in this case, we need to rotate the axis to match acceleration. So my acceleration is going to equal g sine theta, if you remember from our ramp days. When theta is small, sine theta is going to pretty much equal theta, or x over L, where L is the length, x is the horizontal displacement. Okay, so A of t is going to equal minus g theta t, realizing that theta of t, like I said, is really going to be x of t divided by L, and reorganizing it becomes minus g over L x of t. Following the same approach that we did for the mass spring, period turns into 2 pi times the square root of the length of the pendulum divided by g. Understand this is a simple pendulum where we have basically a massless rod or a string and then a weight on the end. We'll talk about a physical pendulum in a few slides. Okay, just to go over the small angle approximation, this is a table of the small angles from 1 to 20. In general, if you look at 10 degrees, the number of radians in 10 degrees is 0.1745. Sine is only going to be 0.1% off from that, which is pretty good. Okay, even going up to 20 degrees, we're only 0.7%, less than 1% difference. Okay, so some people say 20 degrees is fine. I usually use 15. Some people use 10, but understand as long as it's a relatively small degree, that's pretty good. I probably wouldn't want to go too much above 20, if at all. Okay, so here's some practice. This is a torsional pendulum where the springiness is in the turning of the wire that this object is hanging on. Okay, so in this case, torque is going to equal minus k theta. Okay, I want you to go through the same process that we did to derive the period. I will, so pause it at this point and try that. If you pause it after every step, it's kind of like acts as a hint. So I'm going to go through this relatively slowly and try and pause it if you need to figure it out on your own. So the first thing, like I said, torque is equal to minus k theta, but we also know torque is equal to I alpha. So this is similar to F equals ma. Okay, so alpha turns into d squared theta dt squared, and that's going to equal minus k theta. Next, we guess, or basically say that theta of t is some amplitude times cosine omega t. It doesn't matter if you use sine or cosine. From there, we'll go to alpha of t is equal to minus a omega squared cosine omega t. Basically, we took a second derivative. We basically find that omega squared now equals minus k over I. And omega, therefore, is a square root of k over I, and period turns into 2 pi times the square root of I over k. Here's again, more practice. This is a physical pendulum where the rod is no longer massless. Okay, in fact, it doesn't even have to be a rod as it is in this case. It could be any shape. In this case, the center of mass of the object is located a distance r from the point of rotation. So, calculate the period t. Again, follow along slowly, pause when you need to. Again, my torque is going to equal I alpha, and torque is going to be equal to force times distance, or basically mg sine theta times r, and that's going to equal I alpha. You will need the small angle approximation, so apply that. That basically turns this into mgr theta equals I alpha. Alpha, as we've seen before, really becomes minus omega squared theta. Well, that basically says that omega is going to equal the omega squared is mgr over I, and period is 2 pi times the square root of I over mgr. For the last state of practice, okay, I want you to work with two springs, okay? The springs will have a constant K1 and a K2. On the left, springs in series. On the right, springs in parallel. Calculate the period for these and calculate the equivalent spring. We did this when we did resistors sophomore year. Just understand that delta X for, so we're going to replace both resistors with we're going to replace both springs with one spring. In the case of the series, delta X for that equivalent spring is going to equal X1 plus X2. And on the parallel side, delta X is going to equal X1 equals X2. Okay, so see if you can do that, and we'll review this in class. Thank you.